Well, hello. What's up? I hope that you're all doing very well and enjoying learning. I'm your personal physics tutor, Dr. Rima McMullen. In today's lecture, we are going to go over what is scientific notation, what is the importance of scientific notation, and how do we write a number in scientific notation. We will also look at how we can tell how many number of significant digits are in a number that is written in scientific notation. Alright, so let's begin our lecture. Scientific notation is a very convenient way to write numbers that are very large or very small. For example, let me write some numbers over here. Let's say we have a number 0.0000532 centimeters. So quite a few zeros, huh? I could write this as 5.32 times 10 to the power minus 5 centimeters. Now, on the right hand side, this number is written in scientific notation. This is scientific notation. While on the left hand side, the number is written in its original expanded form. So you can see for yourself that when the number is written in scientific notation, like on the right hand side over here, the number becomes very compact. The number looks very tidy and neat when written in scientific notation. Now this was an example of a number that is very small. Next, let's look at a number that is very large. So let the number be 2, 3, 4, 5, 6, 7, and 8. 300 million per second. Now this happens to be c, the speed of light in vacuum. This can be written as 3 times 10 to the power 8 meters per second in scientific notation. And once again, you see that on the right hand side, when I write the speed of light in scientific notation, it is quite compact. So it's very easy to carry out calculations when the numbers are written in scientific notation. They are compact, they are tidy, and makes calculations much easier. You will see as the lecture progresses and as we go over more lectures how scientific notation makes our life very easy. Alright, so we already said that scientific notation is a very convenient way to write numbers that are very large or very small. In scientific notation, a number is written as a times 10 to the power b. Now just a few slides back, I showed you examples of a couple of numbers written in scientific notation. One was, I believe, 5.32 times 10 to the power minus 5. And the other one was 3 times 10 to the power 8. This was in centimeters, the first one, and the second one was in meters per second. Now, if I compare these two numbers with the generic form of scientific notation, which is a times 10 to the power b. Then when I compare a times 10 to the power b with this number written over here, then obviously this 10 over here equals this 10. That says that this b must be equal to minus 5. And if this factor equals this factor over here, then 5.32 must be equal to a. So a is equal to 5.32. And a is called as the coefficient of number written in terms of scientific notation. Alrighty. Now, in the second number that is written in terms of scientific notation, what do you think A is? And what is B? So once again, compare this with A times 10 to the power B. So obviously A is equal to 3, 10 is equal to 10, therefore B must be equal to 8. So A is 3 and B is equal to 8. So I hope that it's easy for you to tell, to identify when a number is written in scientific notation, which part of the number, which factor is A, the coefficient, And once you identify the coefficient, the remaining part must be 10 to the power b. A. Now this a, the coefficient, it can't have just any random value. It must lie within this range. A must be equal to or greater than 1, but must be smaller than 10. Okay. So a will always be some non-zero digit dot the decimal followed by some other digits. And after the decimal, you could have any number of digits. Okay. Alrighty. Next, scientific notation is a very convenient way to communicate significant figures in a number. How so? Well, it turns out that all the digits in the coefficient a are significant. How? I'll show you how. Let's look at some examples. 5.23 times 10 to the power 9. So, here, what's the value of a? 5.23. What is b equal to? 9. How many sig figs are in 5.23 times 10 to the power 9? Well, you just saw here that all the digits in the coefficient a are significant. So over here, this is your a, which is 5.23. And you can see that 5.23 does lie within this range. It is equal to or greater than 1, but smaller than 10. Alrighty. And how many digits are here? 3. And all of those digits are significant, because that's our rule. But how so? Let's look at that. Now, 5.23 times 10 to the power 9. I have expanded it, and it becomes equal to 5,230,000,000. So all the trailing zeros over here, they are yellow. Now the rule is that, which we did in lecture number 1, and if you haven't watched lecture number 1 on significant figures, where we learned how to tell how many number of sig figs are there in a given number, you should watch that lecture before watching this one. What I'll do is I'll put the link for that lecture in the description for this one. Alrighty, so in lecture number 1, we learned that the trailing zeros for whole numbers are not significant. So on the right hand side, this number 5,230,000,000, this is a whole number. And all these zeros, and whether how many zeros, there are a total of 7 zeros here, they're all not significant. They're insignificant. Therefore, if the trailing zeros are insignificant on the right hand side, then the significant digits must be these one. And how many of them are there? 3. So now I'm going to make a claim that if there are 3 significant digits on the right hand side, then the left hand side must contain only 3 significant digits. Let's look at the number written on the left hand side. On the left hand side, the number is written in the form of scientific notation, which is a times 10 to the power b. So here, a is equal to 5.23 and b is equal to 9. Now in this coefficient a alone, there are 3 digits. And these are significant. So on the right hand side, we already know that there are 3 digits that are significant. Therefore, we made a claim that on the left side as well, I should have only 3 sig figs, and the coefficient a alone has 3 digits. That implies that this factor, which is 10 to the power b, in this case 10 to the power 9, does not have any significant digits. Therefore, all the significant digits in a number that is written in form of scientific notation must be in the coefficient a alone. I hope that this little argument made sense. Alrighty, moving on. So, just a repetition of what we did. Repetition really helps the topic sink into the brain. So, number of sig figs on the right hand side, 1, 2, and 3. 3 sig figs. Therefore, on the left hand side, there are 3 sig figs that are all in the coefficient a. So, once again, scientific notation is a very convenient way to represent numbers that are either very large or very small, or both. And secondly, all the the digits in the coefficient A of the number written in scientific notation are significant. Alrighty. After this, we're going to look at several examples now. 0.00000, too many zeros, I lost track, followed by some non-zero digits, then a zero, then again some non-zero digits. Alrighty, let's go ahead and write this number in scientific notation, and there it is, 9.50183 times 10 to the power minus 7. So look at this A, the coefficient, and you can see for yourself that it indeed lies within this range. Okay. So we're going to say how many sig figs are in the number above. What do you say? 1, 2, 3, 4, 5, and 6. Now you might ask about this zero. Well, this zero happens to be a captive zero. What's a captive zero? We learned about that in lecture number 1 of this playlist. So there's 6 sig figs on the right hand side. Therefore, there are 6 sig figs on the left hand side, which we know from the lecture number 1 that if a number is written in this form, it's beginning with a 0, then a decimal, then several zeros, 1 0, 2 zeros. These zeros in front, these are called as leading zeros. And leading zeros are not significant. Therefore, only these digits, once it starts out with this non-zero, following, however many number of digits are there, all of these are significant. Alright, very well. Next, we are going to learn how do you convert a very small number that is smaller than 1 over here into scientific notation. Okay, so this number, this is obviously much smaller than 1. So therefore, we need to bring it within this range. And to do that, we need to move the decimal over. The decimal must move to the right. And it should come from here to between 8 and 3. So what I'm going to do is I'm going to count by how many places did I move the decimal over to the right. 1, 2, 3, 4, and 5. So the decimal needs to move over to the right by 5 places. I'm going to write down this number now, 0.000083 and 4. Next, what I'll do is I'm going to multiply this number with 100,000. Why 100,000? Because when I multiply this number with 100,000, it changes to what? 8.34. And 8.34 is within this range, right? But here is the problem. My number that I'm trying to represent, it is far, far smaller than 1, while when I multiply it with 100,000, it changes to 8.34. So my original number is obviously not equal to this new number. So I need to do something such that this number on the right hand side equals this original number. And you know by now that I need to multiply this with 10 to the power b. So essentially, I'm trying to figure out what b is. Okay, I see that I'm cutting off this 10 to the power b. Hang on, I'll fix it. So essentially, we're trying to figure out this b. Fine. So if I'm multiplying this original number by 100,000, I will go ahead and divide it by 100,000 as well. Okay. And by doing so, I'm essentially multiplying my original number with number equal to 1. And that changes nothing. So now what is this b? That's still a question. Now 0.0000834 times this number at the top, which is 100,000, can be written as 10 to the power 5. And the number at the bottom is also 10 to the power 5. Now these 5 zeros over here that are following 1, they came from over here. I moved the decimal over by 5 places. That's why I multiplied the original number by 1 followed by 5 zeros. and also divided by 1 followed by 5 zeros. 1 followed by 5 zeros, that is 100,000, can be written as 10 to the power 5. Now, next what I'm going to do is I'm going to use up this 10 to the power 5 at the top and multiply it with 0.0000834. That will give me 8.34 divided by 10 to the power 5. Now I can bring this 10 to the power 5 up to the numerator. When I bring a number to the numerator, the power of the number changes, so it becomes minus 5. So b is equal to what? Minus 5. Did it make sense? I hope so. So let's see. Here's the example number 1. We're given the number 0.0000834 and we want to convert this into scientific notation. So we need to move the decimal over to the right. By how many places? 5 places. So when we move the decimal over by 5 places, the number changes to 8.34. All of these leading zeros, they do not count. And I'm going to multiply this 8.34 with 10 to the power negative 5, which is same as dividing 8.34 by 10 to the power 5. And when I divide 8.34 by 10 to the power 5, I get 0.0000834. So I think one thing that can be tricky for some students is figuring out whether to multiply this with 10 to the power minus 5 or plus 5. So here's one way to do. You're going from a very small number on the left hand side to a larger number. I mean, this number is larger than the number on the left hand side. It's still not a very big number. It's still less than 10. But we need the right hand side to be actually a small number. So it's equal to same as left hand side. Therefore, we must multiply the number on the right hand side by a small number. And 10 to the power negative will be a small number. 10 to the power positive will be a big number. You get that? I'm sure you do. Let me know in the comments, if something is not clear, if something could be done better, anything I could do better, I'll try my best. Alrighty, so here's our answer. 8.34 times 10 to the power negative 5. So leading zeros are not significant. All these zeros are not significant. How do we know? We learned that rule in lesson number 1, in lecture number 1 of this playlist. So on the left hand side, I have 1, 2, and 3. 3 sig figs. Therefore, on the right hand side, I must have only 3 sig figs. And once again, like we did before, all of those sig figs are here in the coefficient because coefficient alone has 3 digits. Therefore, they must also be significant. And 10 to the power whatever is there, that is not significant. I know I'm kind of going like a little broken record, but repetition is extremely important. That's why I'm doing this. Alrighty, leading zeros are not significant. Therefore, we have total of 3 significant digits for this number. Every digit in the coefficient A of a number written in scientific notation is significant. Cool? Yep. With that, we move on to example number 2. Again, a number that is smaller than 1. So, 0.001784. Which way do I need to move the decimal? The decimal needs to move over to the right and come to lie in between 1 and 7. That will make this number 1.784, which lies within this range. Alright, so decimal moves over by 3 places here. So let's begin with our original number 0.001784. I am going to multiply this number with 10 to the power 3 and also divide it by 10 to the power 3. How come 10 to the power 3? Well, it will always be 10 to the power something. What is that power? That is determined by how many places you're moving the decimal. Okay. Now, since this number is smaller than 1 that we're trying to write in scientific notation, this 10 to the power 3 at the top will multiply the number and convert this to 1.784, and this will be divided by 10 to the power 3. Next, we are going to bring the number at the bottom upstairs and its power will change. So the number becomes 1.784 times 10 to the power negative 3. So here A is 1.784 and B is minus 3. Cool? Let's see. Once again, we're moving the decimal over to the right by how many places? 3 places. This makes the number 1.784 times 10 to the power minus 3. Very good. How many significant figures or digits are there in this number? Now, what do we know? That all the digits in the coefficient A are significant. So there are a total of 4 significant digits in this number written in scientific notation. So there are 4 sig figs, very good. Now we're going to round it off to 3 sig figs. To do that, okay, I rewrote the number in such a way that there is this line here. This line has 3 digits on the left of it and 1 digit on the right. Why 3 digits on the left of this line? Because I'm trying to round off to 3 sig figs. Okay. Next, what I'm going to do is I'm going to look at the digit immediately to the right of the line that I drew here. This is my line. And that number is 4. So if that number is less than 5, then the number to the left of the line, it remains itself. But had this number to the right of the line been 5 or greater, then the number to the left of the line would have rounded up by 1. Well, if it doesn't make sense yet, wait, it will, because we are going to go over so many examples. So let's see. This becomes 1.78 times 10 to the power minus 3. And it has 3 sig figs now. Next, we are going to round off to 2 sig figs. Now I'm drawing this line between 7 and 8. So there are 2 digits to the left of it. So all I'm concerned about is how many digits are to the left of the line. To the right of it, there can be as many digits as, doesn't matter. Since I want to round it off to 2 digits, I must have only 2 digits to the left of this line that I've just drawn. Okay. Now, you might ask, does this number here matter? This digit? What if this digit had been, 1.78 and, What if? Wait. What if this number had been 1.748? What would you round it up to? Okay. I want to round it to 2 digits. So do I see that there's this 8 here? So when I take away this 8, this 4 becomes 5. And now since this is 5, the 7 becomes 8. And therefore the answer is 1.8. Absolutely not. That would be wrong. Why I'm telling you this? Because there was a time when I did this wrong. And why I did that wrong? I guess I hadn't paid attention yet. So I had to learn it the right way. I did. So here in 1.748, this is the 10th place. 4 is at the 100th place. Okay, let's write it over here. 1.748. 10th place, 100th, 1000th. Whatever is happening at the 1000th place, that doesn't have much impact on what's happening at the 100th place, right? So if I had to round it off to 3 digits, then this 8 would matter. But when I have to round it off to 2 digits, then this 8 that's at the thousandth place has no impact on the 7 on the 10th place. Okay. If I were to round it off to single digit, one digit, then this 8 and 4 will both have no impact. Only the 7 will have impact. So if you're rounding off to two digits, then only the third digit will have an impact on rounding off. If you're rounding it off to, let's say, nth digit, then only n plus 1 digit will have an impact. All the digits after that will have no impact. Okay. So if a number is 7 digits long, 7, 8, 9, 2, 3, 4, 1. If I have to round it off to one significant figure, then only this 8 matters. Okay? To round it off to one significant figure, you will put the line here. Only 8 matters. If I wanted to round it off to 2 significant figures, then only this 9 matters. Nothing else matters. Okay? If I were to round it off to 3 sig figs, then I'll look only at this number. I'll disregard all of these over here. I hope it made sense by now. If it didn't, let me know in the comments and I'll try to do a better job. Round it off to 2 sig figs. 8 is greater than 5, therefore 7 rounds up to 8, not to 9. It's a typo over here. Alrighty, which I'll fix in the next slides, but that slide somehow got overlooked. So our answer is 1.8 times 10 to the power negative 3, 2 sig figs. Quite easy? I think so. Example number 3, 0.0018954. So I'll show you once again how to convert this into scientific notation. This number is again less than 1. And this is going to be the last example of a number that is smaller than 1 that we're converting into scientific notation. In the next example, we're going to look at a number that's going to be greater than 10. Alrighty, so which way do you move the decimal over to? Of course, to the right. By how many places? 3 places. How do I know that there are 3 places? Because the decimal is over here, 0.01894. When I move the decimal over here, there are 1, 2, and 3 digits between this present location of the decimal to wherever I'm going to move the decimal. Alright, so let's write down our number, 0.0018954 for 3 places. Multiply this number with 10 to the power, this 3. And if I multiply by something, then I have to divide by that number as well. Why so? Because together this makes 1, and multiplying any number with 1 changes nothing. Go ahead and multiply the number with 10 to the power 3 gives us 1.8954 divided by 10 to the power 3, which can now be written in scientific notation as, 1.8954 times 10 to the power minus 3. Okay. Round off to 4 sig figs. Alright, we'll do that, but before that, how many sig figs do we have to begin with? 1, 2, 3, and 4, and 5. So the original number has 5 significant digits. Digits. Alrighty, I'm going to draw this line, and to the left of the line, how many digits would we have? 4. Why? Because we are rounding off the answer to the 4 digits. Very well. To the right of the line is 4, and 4 is less than 5. Therefore, the number to the left of the line, which is 5, remains 5. So our answer is 1.895 times 10 to the power negative 3. There are 4 significant digits here. Next, we are going to now round off to 3 significant digits, the original number. Again, draw a line. Now there are 3 digits to the left of the line. And when we're going to round it off, we're going to look at only that digit that's to the right of the line. We're not going to worry about this 4 at all. Pretend like this 4 is not even there. Okay? So since that digit to the right of the line is actually 5, the digit to the left of it, which is 9, changes to 10. Alrighty. So now what would this number become? Let's see. Let's say you have, let's say 1.89. It can be written as 1 plus 0.89, and 0.89 can be written as 0.80 plus 0.09. Correct? Grade school mathematics. This I can write as 0 plus 0.80, but now we're going to say that this 9 is changing to 10. So it becomes 0.10, correct? Now add these numbers up. It becomes 1 plus 0.80 plus 0.10, 0.90 gives you 1.90 here. So this is your answer, of course, times 10 to the power negative 3. Just wanted to show you explicitly how to round it up, how it makes sense. It's important to make sense of things. It's important to understand things in physics and chemistry and mathematics, because if you don't really understand it, you can go only so far. I don't claim to understand everything, but I try my best. And whatever I understand, I'll try my best to convey it to you. I'll try to make these lectures as intuitive as I can. So that's my goal, to make things intuitive, so it just, sinks into your soul. Next, we are going to round off to 2 sig figs. So just like before, we're going to draw the line such that there are 2 digits to the left of this line over here. Again, pretend like this 5 and 4 are not there. Okay. Look only at the digit to the right of the line, which happens to be 9. And 9 is obviously greater than 5, so the digit to the left of the line, which is 8, rounds up to 9. So our answer is 1.9 times 10 to the power minus 3. 2 sig figs. Here it is. I see that the last one is partly hidden, but here it is, 1.9 times 10 to the power negative 3. Cool. So cool. Next, how do you convert a number, this h, and how is little cutoff? Here we go. How do you convert a number x, which is greater than 10, to scientific notation? No biggie. Here we go. Example number 4, 7459.84. Alrighty. Now, you need to bring this big number, which is bigger than 10, to lie within this range. So it needs to be smaller than 10. To make this number smaller than 10, you need to move the decimal to the left over here, such that the decimal now lies between 7 and 4. So by how many places are you moving the decimal over to the left? To determine that, count the number of digits between the location where the decimal is to where you're going to move it over to. So they're like 1, 2, 3 digits. You're going to move the decimal over by 3 places. Alright, so just like before, write your number, multiply it with 10 to the power 3 divided by 10 to the power 3. Why this 3? Because there are 3 digits between the 2 locations of the decimal. In other words, you're going to move the decimal over to the left by 3 places. Therefore, I'm multiplying the number by 10 to the power 3. But you can't just multiply a number by anything. You can multiply it by 1. Multiplying by 1 changes nothing. But multiplying it with just only 10 to the power 3 changes a lot. Okay? It increases the number by 3 orders of magnitude. So I'm also going to divide it by 10 to the power 3. Together these two, this is equal to 1. So multiplying by 1 changes nothing. Now the question is, out of this 10 to the power 3 at the top and the bottom, which one am I going to utilize? So since I want to make this number smaller, we will divide it by 10 to the power 3. So that gives you 7459.84 divided by 10 to the power 3 times 10 to the power 3. And this one is this over here. This 10 to the power on the left side is at the bottom here. So this gives me 7.45984. That's what the division gives me, times 10 to the power 3. And here you go, your number has been written in scientific notation. So we're moving the decimal over to the left by 3 places. The number becomes 7.45984. This number is smaller than the number we started out with. Therefore, we are going to multiply it with 10 to the power, a positive number. So together, this can give us a large number, which is on the left-hand side. Cool? Yep. How many sig figs are there in the number above? 1, 2, 3, 4, 5, and 6. 6 significant figures. Now we're going to do some rounding off. Round it off to 5 sig figs. Put this line such that there are 5 digits to the left of the line. Then look at the digits to the right of the line, which is 4. So 4 is smaller than 5, therefore it changes nothing. The 8 to the left of the line remains 8. So there you go. The answer is 7.4598 times 10 to the power 3. Here you go. Next, we are going to round it off to 4 sig figs, the original number. Alrighty. Now, please do not begin with this number. Okay, do not go from here to here and then from here to here. That can give you wrong answer. May or may not. In this case, it won't, but it can. Alrighty, here's the line. 4 digits to the left of the line, and the digit to the right of it is 8. Which is not less than 5, it is more than 5. So the 9 rounds up to 10. Typo. Greater than 5. That's what happens when you copy and paste things. My bad. But we caught it more. Greater. Okay. I pay attention, at least when I'm lecturing, huh? Alright, when you round it up now, that 9 rounded up to 10. Okay, and I already showed you one example where we went from 1.89 to 1.90. Let me show this to you again. 7.459. We're saying that this 9 will round up to 10, correct? But this number, 7.459, can be written as 7 plus 0.400 plus 0.050 plus 0.009. Now, this 9 over here, this is going to round up to 10. So it becomes 0.10. Plus the remaining numbers remain the same. What do I get? This will give you 7.460. Here you go. So that's how it rounded up. Got it? You did. Okay. Now round off to 3 sig figs. Again, put this line over here. To the left of the line, I have 3 digits. Why? Because I want to round off to 3 sig figs. Okay. So we're going to pretend like this 8 and 4 are not even there. 9 is greater than 5. Therefore, the number to the left of the line, which is 5, rounds up to what? 6. Therefore, our answer is now 7.46 times 10 to the power 3. Next, you're going to round off to 2 sig figs. Okay. Put the line such that there are 2 digits to the left of the line. Pretend like these last 3 digits, they don't matter here. Okay. These don't matter. 5, the digit to the right of the line, it's 5. So the digit to the left of the line, which is 4, now rounds up to 5. And our answer is 7.5 times 10 to the power 3. Easy. Example 5. Again, given a number larger than 10. So by how many places do you need to move the decimal over to the left? 4 places. So 1, 2, 3, 4. 4 places. Write down the number 83912.34 times 10 to the power, that's 4 over here, divided by 10 to the power 4. So we are going to use the 10 to the power 4 at the bottom, and this 10 to the power 4 at the top just stays as is. This division gives us 8.392.34. Did I say point again? 8.39234 times 10 to the power 4. There the number is now written in scientific notation. A lies within this range. A is 8.39234 and B is equal to 4. Alrighty. So we're going to move the decimal over to the left by 4 places. Therefore the answer is 8.391234 times 10 to the power 4. How many sig figs are there in this number? 1, 2, 3, 4, 5, 6, 7. 7 sig figs. Round off to 6 sig figs. Okay. Draw this line. To the right of the line there's only 1 digit and that digit is less than 5. So therefore the number to the left of the line remains as is, and that is rounded off to 6 sig figs now. Okay. Next, round off to 4 sig figs. So I draw this line such that there are 5 digits to the left of the line. Now since there are 2 digits to the right of the line, ignore this last digit. It does not matter. Whatever remains though is 3, and that is less than 5. Therefore the number does not change. It remains, therefore the number to the left of the line does not change and it remains 8.3912 times 10 to the power 4. Round off to 4 sig figs. We have this line. We have 4 digits to the left of the line. To round this up, you're going to ignore 3 and 4. You're going to look only at the digit immediately to the right of the line. That happens to be less than 5. Therefore, once again, the answer is going to be 8.391. Nothing really has rounded up. Round off to 2 sig figs. Okay. In this case, in this example, I'm not rounding off to 3 sig figs. You can if you want. So draw this line such that there are 2 digits to the left of it. Ignore the 4 last digits. Okay, they don't matter. The digit to the right of the line is 9, which is definitely bigger than 5. Therefore, the digit to the left of the line, which is 3, rounds up to 4, and our answer is going to be 8.4 times 10 to the power 4. Okay. Alright, so we looked at several examples of writing a number in scientific notation. We looked at what scientific notation is, what is the coefficient of the scientific notation, and what the power is. And all of the significant digits in a number are contained in the coefficient A. Then we looked at several examples of converting a number less than 1 into scientific notation, and also numbers that were greater than 10, they were converted into scientific notation. I'm going to repeat that strategy once again here. And in addition, we also looked at how to round off numbers, okay, to a certain number of significant digits. Alrighty. So once again, if you want to round off a number to a certain number of significant digits, okay, so this number has 1, 2, 3, 4, 5, 6 digits, whatever random digits are there, let's say. And we want to round off to 2 sig figs. So you're going to put this line over here and you're going to disregard these numbers. Okay, they don't matter. These will just automatically become zeros here. Okay, you're going to look only at this number, and based on this number, if this is 5 or greater, the number to the left of the line will round up. If this number here is less than 5, then this number to the left of it, the left of the line, remains itself. Did you already know this? I would think so. Alrighty. Example of converting into scientific notation. Alright. Example. Quick review of how to convert a number x less than 1 into scientific notation. Let this number be what? 0.002893. So first thing is the decimal needs to move over to the right by 3 places. I will write down the number 0.002893 multiplied by 10 to the power 3 divided by 10 to the power 3. The 10 to the power 3 will actually multiply the number and give you 2.893, and this 10 to the power 3 from the bottom, it remains as is. So next what you're going to do is bring this 10 to the power 3 from the denominator to numerator, and its power will change its sign. That's all that you have got to do. Done. So that's the strategy for x less than 1 when you're converting a number smaller than 1 into scientific notation. Next, look at an example of a number greater than 10 that is now converted into scientific notation. 983.24. Okay. So this number is obviously greater than 10. I need to move the decimal over to the left, so it now lies between 9 and 8. So 2 places. Decimal moves over by 2 places. Okay. So original number 983.24 times 10 to the power, what do you write here? This 2 over here. And divided by 10 to the power 2. Now in this case, you're going to use this 10 to the power 2 at the bottom. This will divide the original number. 983.24 divided by 10 to the power 2 times 10 to the power 2. This will give you 9.8324 times 10 to the power 2. There you go. Done. Alright. So in the next lecture, we're going to look at 2 things. In the next maybe couple of lectures. I don't know if this will be all in one lecture or I'm going to make it in 2 lectures. But what we're going to do is we're going to look at how mathematical operations are performed with significant figures. In other words, if you have a few numbers on which you're applying some mathematical operations like addition, subtraction, multiplication, or division, then how significant digits are carried on in the calculation, how significant digits propagate in calculations. So that's going to be very important. And next we're going to look at algebra of scientific notation. How do you do addition, subtraction, multiplication, division in numbers that involve scientific notation? And we'll also look at how to take the natural log and exponentials, etc. of the numbers that are written in scientific notation. That will be in next 1 to 2 lectures, and those lectures should be coming up in next maybe 4 to 7 days. That's about how long it takes to make a lecture for me. I mean, I have a full-time job. This is my part-time hobby work that I really enjoy doing. I'm counting on you guys to make it successful, cooperate, give me feedback, let me know how you like it, how you want it to be different, how I can improve it. And if you haven't liked the video or subscribed to the channel, please subscribe this channel. That is still in its infantile stage. Alrighty, I'll see you again very soon next time. Until then, stay well, stay cool, and keep studying, keep learning, keep growing. That's the only way to live life. See ya. Bye-bye.